So this is the first episode in a section titled pH and Logarithms. I actually got the inspiration for this from the eponymously titled section of Enrich, specifically the chemistry section, Chem Enrich, pH and Logarithms. And so I thought that we'd take a look at the first few questions that sort of gave me inspiration for this whole idea. And I suppose I'll sort of start it off, not delve too deep, with a short introduction into actually how logarithms are embedded within our definition of pH and how that actually applies to these questions in particular. So, all these questions center around the central equation of pH equals negative log to the base 10 of the concentration of hydrogen. Now the P in pH actually in itself means something very peculiar. It means negative log to the base 10, and these square brackets around this hydrogen actually symbolize concentration. Now this concentration variable is given in moles per liter. Liter is also known as a cubic decimeter, or dm cubed, more specifically. So in itself here, square brackets H plus would be the concentration of hydrogen plus ions in moles per liter cubed. So if I gave square brackets OH minus, this would be the concentration of the negative hydroxide ion. So if we go into a specific example, so water, pure water is a good example because it has a very specific pH of pH 7 on our scale of 1 to 14. And the reason this is specifically important is because water itself dissociates, or when you place an acid and dissolve it inside of it, water will dissociate. Now this actual chemical reaction is given by H2O. It's a reversible reaction. H2O dissociates into an H plus ion, specifically relevant here for a pH, and OH minus ions. Now in real life this doesn't actually happen. This is because due to the nature of water forming hydrogen bonds with each other, when hydrogen is left by itself upon dissociation, it becomes naturally attracted to a pre-existing water molecule, sort of like this. In this way it creates a H3O plus ion and a negatively charged hydroxide ion. So this H plus ion is never really left on its own. It joins a pre-existing water molecule. And now we know that the pH of pure water is pH 7. This is especially important because we know that one water molecule dissociates into exactly one H plus and one OH minus molecule. So if the pH of water was 7, then we can infer the pOH of water would also be 7 because they dissociate in equal amounts. And from this we can then infer that from our scale of 1 to 14, pH plus pOH will give exactly 14. Now this is especially relevant in other calculations as well, but seeing as all pH revolves around dissolving in an aqueous solution, meaning water or water itself, dissociating, especially at higher temperatures, it will do more of that. It's especially important because knowing either pH or pOH will allow us to calculate the former or latter.